Okay. So today's topic we will talk about logistic regression, and I think simply, logistic regression is actually what we would call like a nonlinear model. And when we say it's nonlinear, that means that we are using like a nonlinear function to map. But simply put it, when we talk about logistic regression, it is like we have input x, right? That was like an input vector, maybe like a feature vector of Rn. And then after that, we do some kind of linear mapping. You can think of what we've tried last time with the linear regression, where we compute y equal to ax, or maybe I think we use like x beta, something like that, but maybe x transpose beta would be better. Let's say in this case x is like a vector, like a vector of input samples. And let's say a vector of n input sample, actually. Maybe an input vector, that's better, sorry. And let's say we have an input vector, we compute like a linear mapping with the beta, which is like model parameters that we learned. So if we use y as an output and compare that with our measurements, then that will be linear regression. Just to recap, if it was just linear regression, we can compute beta by like a formula where we compute x transpose x inward x. Is that right? I'm not sure. Beta is equal to x inward y. Yeah. Yep. If it was just linear regression. But in this case, when we are extending this to logistic regression, which will convert the output of linear regression into like a classification probability. So this is how we turn from linear regression into like a classification task. So we will use this input y, we will use this output y as the output to like a sigmoid function. And then we get something like a y hat here. Maybe I shouldn't use y, maybe y bar is better, because if we use y as the measurements, then yeah, it's kind of abusing the notation. So if we get the y hat here, y hat here, where we are using it to represent the output from sigmoid function, there are some properties associated with that y hat. The property is that whatever value of y, the sigmoid function will map that value to a value between 0 and 1. That is like y hat, and this is like y bar. So whatever that we get from linear mapping, it doesn't matter. If we pass that through sigmoid function, the sigmoid function will turn this value into a value between 0 and 1. So that is the output of the logistic regression. That's what we want to learn today. What is the importance of logistic regression is that whatever we get as the output here, since it's a value between 0 and 1, immediately, if we use a thresholding of maybe 0.5, you can use this output y hat for classification, like binary classification. But the thing is, this logistic regression, as you might see, since the output y hat is expected to be like a value ranging between 0 and 1, well, the question is, how can we ensure that this output y hat will be representative of the class, right? If we were to use this for binary classification, but if we were to use this output for regression task, which is possible as well because it's a value between 0 and 1. If we were to use this for a regression task, of course we can do something like using like a mean square error to minimize that. But if we were to use it for classification tasks, we have to use different loss function. If you ask me, can we still use this? The answer is probably yes. We can still use this to tune a classifier, but there is, when it comes to the sense of interpretation of this is pretty much just like you want the y hat to be like a binary vector that give you whatever you want. But the problem with that is the lack of the probabilistic interpretation. So that's kind of the reason why we may want to come up with a new loss function. But that's maybe just to give an idea why we use different one. Okay. So what does it look like when it's come to implementation? And you will see this one in the lab. So firstly, when we want to use linear regression, we want to have like a linear mapping. And in this case, we will use like a torch and n. I'm not sure if it's called function, but it's more like a class, neural network class that is linked to the linear layer. After that, we will have to give the output of this linear layer mapping as the input to a sigmoid function. So that's how it's done. Because sigmoid function is a function that is purely defined like this. There is no parameters associated with it. It just receives x as an input. Therefore, the way that we would use this function, we will use it as like an activation function that doesn't have the modal parameters associated. So this is how you may want to use it. And yes, it's the same thing in the lab 3. You can scroll over. Usually when you have like a layer or maybe a neural network that defined like this, the parameters inside the, how should I say, it's like the parameters that was announced inside the init usually will be the one that is going to be the modal parameters. So in this case, only the linear mapping will provide you like a set of parameters, but the sigmoid will just be a function. Okay. So if you see, that is how we compute y hat here, y predict here. And in fact, this y predict will be equivalent to the probability of y, we can say y equal to 1 or 0 given x. The reason that I said is like, it could either be y equal to 1 or 0 is because Okay, let us look at the function. If we want pop of y equal to 0, if we want a pop of y equal to 1, so that is like exponential function like this, right? If this value is very low, like a exponential of a very high negative value, or maybe beta x is very high, then negate, and then this very low, then you get fx nearly equal to 1. But if you have like exponential of something close to 0, very not close to 0. If you have exponential of a number that is very large, let's say that will be, let's say close to infinity, then that will become 0. So that is how we say we map it between 0 and 1. Maybe I don't have like a good graphical showing here, but maybe let's draw a line for this function. Okay, let's draw a line for this function. Okay, so this is like a sigmoid function. It can be used to represent both 0 and 1. And for linear regression, for logistic regression, we usually signal 0 as like a class 0, or maybe the weight for class 0, and 1 for weight for class 1. So I'll put this way. If this is the x value, if x go towards minus infinity, then this will be 1 over 1 plus something really big. So the value will be close to 0. Because it's very big, this is close to 0. And when x is equal to 0, then this will be 1. So that will be 0.5. So it will go somewhere here. And when x is very large, like exponential of minus infinity, very large here, then this will close to 0. Then you have 1. Okay, so that's what you get. That's a sigmoid function. So it's like, as I mentioned before, you can use this function for mapping both when you want to put the weight for class 0 and class 1. Let's say if you want low weight for class 0 and high weight for class 1, you can use like just one function to represent this. And it depends on how your beta would behave. Because the beta here, if we think about this diagram, beta here will be something that control the output for this gx function. And whatever this gx function would be like is like 1 over exponential of minus gx. So yeah, it's kind of like whatever this is, it will impact whatever value that you get from fx. So your fx is strictly 0 and 1. So that's why sometimes people would use it for the probability, because it's kind of imitating the fact that the probability value will lie between 0 and 1. Are they going to use this? Okay, I don't know. Let them be. Okay, so that's like a... Okay, so we have to move.